Hello and welcome. Have you ever looked at something complex, like, I don't know, a lemon, or maybe even a mountain, and just wondered, how in the world would you measure the volume of that? Well, today we're going to unlock that very secret using one of the most powerful ideas in all of mathematics. Let's get into it.
Really think about that for a second. We have formulas from geometry class for things like boxes and spheres, sure, but what about something that's truly irregular? A shape you can't just plug into a simple equation. It seems impossible, right? But it turns out calculus gives us this incredibly elegant way to solve this exact problem.
You see, basic geometry is fantastic for perfect shapes, things like cylinders and cubes. But the real world, from custom engineering parts to bizarre natural rock formations, it is rarely that simple. We need a tool that can actually handle all the curves and complexities of reality.
So here's our game plan for today. We're going to start by moving beyond those basic shapes, then we'll uncover the secret of slicing. After that, we'll learn how to build 3D solids from scratch, explore the calculus toolkit that makes it all possible, and then use it to measure something that seems impossible. And finally, we'll wrap it all up.
This brings us to the core concept, the secret weapon, really. And the idea is just brilliant in its simplicity. If you can't measure a really complex object all at once, what do? Well, you break it down. You break it into an infinite number of incredibly simple little pieces that you can measure.
And this single sentence, right here, is the foundation for everything we're about to do. You can think of it as the master rule. What it's saying is, if we can just figure out the area of any single slice of an object, we can find the volume of the whole darn thing.
And here's what that rule looks like in the language of math. Now, don't let that weird symbol scare you. That big stretched out S shape, that's an integral sign, and it literally just means sum everything up. So this formula is just telling us that the total volume is just the sum of the area of every single tiny slice. That's it. We're just slicing and summing.
And here's the really cool part. The slices can be any simple shape that we already have a formula for. They can be circles, squares, rectangles, even equilateral triangles. This is what makes the method so incredibly flexible and powerful, because you can apply it to all sorts of weird and wonderful solids. All right, now let's see this idea in action. We're going to look at a really common and powerful application of slicing, which is creating 3D objects just by spinning a 2D shape. Okay, picture this. You've got a flat shape drawn on a piece of paper. Now imagine spinning that paper really fast around a line, kind of like a potter spinning clay on a wheel. The path that flat shape carves out as it spins through 3D space, well, that's called a solid of revolution. And you guessed it, we can use our slicing method to find its volume.
Now, to measure these special solids of revolution, we have three main tools in our calculus toolkit. You can think of them like different attachments for a power drill. Each one is perfectly designed for a specific kind of job.
And this table here breaks it down perfectly. You've got the disk method, which is for solid objects, like a vase or a baseball bat. Then there's the washer method, for objects that have a hole in the middle, like a donut or a pipe. And finally, the shell method, which is a really clever alternative for when it's just easier to think about the problem in a totally different way. The disk method is our slicing principle in its purest form when we're dealing with these solids of revolution. With this method, every single slice is a perfect circle, or a disk. So the area of each slice, our A of x, is just that familiar formula for the area of a circle, pi times the radius squared. The washer method is a simple but really powerful upgrade. If our 3D shape has a hole in it, well then each slice looks like a washer, right? So the area of that slice is just the area of the big outer disk minus the area of the little inner hole. Super simple and super effective. Now the shell method, this one asks us to change our whole perspective. Instead of stacking flat coins, I want you to imagine nesting infinitely thin cans inside of each other, kind of like the layers of an onion. We're still summing up a bunch of little pieces, but this time the pieces are vertical shells instead of horizontal slices. It's a fantastic trick for solving some really tough problems.
Okay, so we've got our toolkit. Now for the really cool part, the payoff. Let's use one of these methods to prove a formula that you've probably known for years, but maybe never knew where it actually came from. We're going to measure the impossible and actually derive the volume of a perfect sphere. The process is just so logical and beautiful. We start with a simple 2D shape, a semicircle. Then we spin it around the x-axis. As it spins, poof, it creates a sphere. Now, since every single slice of this sphere is a solid circle, we know exactly which tool to grab, the disk method.
All we have to do is sum up the areas of all those little circular slices, from the far left side of the sphere to the far right side.
And when all the calculus is said and done, there it is. 4/3 pi r cubed, the exact formula for the volume of a sphere. See, this isn't just some random formula that a mathematician made up one day. It is a direct, logical result of applying the slicing method. That's the real power of this technique.
So, we've seen just how powerful slicing is for figuring out what's inside a shape. But what's really amazing is that the same core idea can be tweaked a little bit to measure the outside of an object, its surface area.
The secret sauce here is this clever bit of math right here, the square root term. It's basically the Pythagorean theorem, but applied on an infinitesimally small scale. It calculates the true diagonal length of each tiny little segment of a curve, accounting for how steep it is. So, by adding up all those tiny diagonal lengths, we can find a total length of a curve, and by spinning them, we find the total surface area. It's amazing.
Okay, so let's bring this all home. We've seen how to slice, spin, and sum our way to measuring some incredibly complex shapes. But why does any of this really matter? This quote from our source material says it all, really. This isn't just some abstract math exercise. These exact techniques are used all the time to design things like airplane wings, to calculate the capacity of reservoirs, to model complex physical phenomena, to solve countless real-world problems in science and engineering that simple geometry just can't touch. And that leaves us with one final big thought. This idea of breaking an impossibly huge problem into countless tiny, manageable pieces is one of the most powerful strategies ever devised, and it goes so far beyond just math. So, what overwhelming challenge in your world could you finally conquer if you just figured out the right way to slice it?